blood cells, it's somewhere in their body and inside of their cells. And so the trick is that in order to treat a viral infection with drugs, you have to figure out a way to get your drug inside of the cells that are affected by the virus, but not in the ones that are not. And that, as you might imagine, is very challenging. Or you have to get them to affect the virus only when it's free in the solution, right? And then you can't affect the cells that are already infected. So it's a very complicated thing due to the nature of what it is you're trying to treat. So currently, most of the options, or all of the options, are only effective against certain types of virus because we target a certain thing on a certain type of virus, and none of them eliminate latent infections, which, as you might imagine, is when the virus integrates its genome into our genome. So you can imagine how that would be incredibly difficult of a thing to treat. So entry inhibitors, there's basically drugs to target each part of the pathway of viral infection. So if you remember, they have to be able to enter our cells. If you can target their ability to do so, there are drugs that do that. That would be the ideal thing to do, because then you don't have to worry about too terrible of side effects. Unfortunately, because viruses develop resistance to this pretty easily, their usefulness is limited. Nucleoside analogs, these are the things that we talked about when we talked about HIV. So like AZT, basically what's a nucleotide? It's an A, a C, a T, or a G, right? So nucleoside analogs are things that look like A's, T's, C's, or G's, but it's a weird A or a weird C. And so they indirectly affect polymerase, because polymerase is the thing making the virus babies, right? Making the genomes for the virus babies. And so it incorporates the weird A instead of the regular A, and then the babies become non-functional. And that's how it's able to stop further virus babies to be produced, but it doesn't actually kill the ones that are already there. So non-nucleoside polymerase inhibitors would directly affect polymerase. Non-nucleoside reverse transcriptase inhibitors obviously are only going to be effective in retroviruses, so like HIV, because those are the only ones that have reverse transcriptase. Integrase is another protein that some viruses carry around with it. It's an enzyme that allows them to integrate their DNA into your DNA, so if you can affect that, that's a drug. Assembly and release of viral particles. So if you've ever heard the term H1N1, it refers to a type of flu, right? And the H is hemagglutinin and the N is neuraminidase, and those are two types of markers that are on those particles. And so neuraminidase inhibitors, of course, would then only be effective against what type of virus? Well, influenza, because that's the only one that has that particular marker. And again, before I leave this category, I just want to make the point that a lot of times if you have a viral infection and you go to the doctor, what do they do for you? They tell you to get plenty of fluids and plenty of rest and, let it run its course. When do we give? We only give antivirals in the case of a really nasty infection where the infection presents more of an issue than the side effects of the medication, right? So for something like a cold or a mild flu, the side effects would be too great to make any sense. You'd be worse from the drugs than you are just suffering through the virus. Antifungals, again, if you look at what it is that you're treating, it makes sense to you that it would be more difficult to develop an antifungal than it would be to develop an antibacterial. Why? Because it's a fungus. What is a fungus? It's a eukaryote, right? Bacteria are prokaryotes, we are eukaryotes, so we have more in common with a fungal cell than we do with a bacterial cell. So first of all, it's going to be harder to develop the drugs. Second of all, they're what? They're going to have more toxic side effects, right? And a higher percentage because they have more interaction with our cells as well. And sure enough, my son had this nasty ringworm infection on his head when he was a baby that wouldn't go away, and I had to give him this griseofulvin stuff, and let me tell you, that was no fun at all. So I think this is, this is the thought that I ended on, which is unfortunate because it's kind of a sad thought to end on, but it's one that is very true. Antiprotozoan and antihelminthic drugs, we have very few. The ones that we have interfere with biosynthetic pathways or the neuromuscular function of worm, and it's kind of a last resort. Like, if you are dying from this infection, then we might try and give it to you. The drugs, they're nasty drugs. And the sad but true reason that we don't have better drugs is partly to do with, yes, it's hard to treat protozoan and helminth because those are eukaryotes and they have more in common with us. But really what the reason for this lack of drugs in this category is because the people who are dying from these infections aren't Donald Trump. The people who are dying from these infections all around the world and suffering from these infections cannot afford the drugs that would be required to cure these conditions or to treat these conditions, and therefore the multi-trillion-dollar drug corporations do not have any motivation to develop or manufacture drugs for these conditions. So that's it. Good luck. As always, if you have any questions or concerns, please let me know. Thank you. Bye.